Sí.
Pues hay mucha gente del sitio que estoy ayudando, aquí estoy 8 personas, ¿no? Sí, en título de 8 personas, sí.
Todo es in der Traum, ja, davon haben wir Wünsche.
Sí, posiblemente tengas que girarlo a la derecha.
Sí, ja, ja.
Sí, y ahora ya darle pantalla completa.
El proyector es demasiado bueno, porque se ve toda la resolución. Muy bueno. El proyector peor.
Vale, a ver, no estoy viendo eso porque está escrito. Entonces tienes que dejar de compartir y compartir el PDF.
Vale. Vale, os dejo, ¿vale?
Vale.
Sí.
Vale.
Tienes que dejar de compartir.
No se ve.
¿La gente en remoto nos oye?
Sí, se oye bien. De vez en cuando hay eco, ¿eh?
Tienes que subir el volumen de la sala. ¿Nos oyen? Sí, sí, se oye.
Se oye bien. De vez en cuando hay eco, ¿eh?
Vale, vamos así. Tienes que subir la sala. Ahora, lo que solo falta ver si se oye por YouTube. No, ya está, ya se oye. Ahora, lo único que quiero ver es si se puede ver en YouTube. No, ya está, ya se oye. Ahora, lo único que quiero ver es si se puede ver en YouTube.
Qué calor, ¿no?
No, ya está, ya se oye.
¿Entramos? ¿Entramos? Sí.
Buenas, ¿qué tal? Hola. Hola.
I guess it's an extended screen, so let me just see if I can. There it is. All right.
Me ha intimidado, así que sí.
Okay, so I will introduce quickly Sven. We at IFCA we know him very well. You will see why now. Thank you first of all for coming from Madrid. He's also from Madrid and he's driving back today just to meet you. There's no volume. So he finished his PhD in Kathmandu in 1998. That's interesting. And then he did postdocs in Delphi and in Brookhaven National Lab, then in the week actually so then he became a harmonica high, and he actually spent several years, 10 years. He finished a PhD in Kathmandu, and then in 2016 he moved to the People outside. He's an expert on the harmonica about his terminology.
Hablo español, pero prefiero dar las clases en inglés. Y si tenéis preguntas, podéis hacerlos en español, en inglés o alemán, da igual. Y a veces tengo preguntas para vosotros, ya vais a ver, están marcados especialmente. Y si habéis venido hace un año ya, o hace 2 años, cuando en mi última clase, pero hace mucho tiempo, hay bastante overlap entre nosotros, pero espero que entre y así. ¿Podemos?
Sí, some people say that they can hear you very well, but I just try to see if it's a general problem or just problems.
Okay, no problem. Bueno, ya tenemos algo aquí, deja funcionar en la distancia.
Yeah. You could click on the PDF. Yeah.
Yes, I will first. Sorry for my voice. Let's say we had a longer party on something, but I hope it will be okay. I will first tell you about the standard model and Higgs, and I will tell you why the standard model is not enough to describe everything. I will come to my favorite rescue, namely symmetry, and since some people are making false claims, I have here one section which is called "Is smoothie dead?" And you know, of course, if such a question is posed, the answer is no. Good, let's get started. If I could.
No. Yes, they say that they hear him, but not very well. I don't know if it is a problem being loud or with noise. Not clear yet. Volume reasonable, but a bit of noise.
Sorry. The standard model. The construction principle of the standard model is spatial invariant. The Lagrange should be invariant under certain symmetry. And the first and most simple example is quantum electrodynamics, where one describes in the first approximation the interaction between an electron and some charged particle via the exchange of the photon here. So the field quanta that is exchanged for this force is the photon. And the Lagrangian that one can write down is very simple. Let's start with the second term here. This here is the fermion. It's also the fermion. Then we have the mass term here with the M. This is the kinetic term for the fermion. And this is the kinetic term for the photon. Now, this du is not only the normal derivative, but actually contains the force field. All this comes from the construction principle. Details are not really relevant by now. If you want to really learn details, there are dedicated courses that will explain this to you. But this is a very simple and construction principle for this kind of Lagrange. So fermion with the kinetic term, where the kinetic term, the force field is included, and then the kinetic term for the force field itself. Good. Now, the QD Lagrangian should be invariant under this U1 gauge symmetry, and how the U1 gauge symmetry acts on the fermions and on the photons is spelled out here, and everything works out fine. So if you take these two transformations, you plug them in here, you will get out the same Lagrangian. Works. Now, what happens if you introduce a mass term for the photon? Yeah? You put here just the mass term. So when I talk to students who see this for the first time, I think because I just with Nestor, I discussed it the other day, why is this a mass term? If this is not clear to you, it's not your fault. It's just something that is so natural that so you look at the propagation of a particle. So you have the particle on the two sides, and then this propagation is driven by the term that controls exactly the propagation from the particle to itself, and therefore it's particle times particle, and then it's mass. This is, as I said, the most important thing if you look at it for quite some time. And if you apply now these transformations on this equation, and you take this one, and you apply this, you get out the original term, but you get out also two extra terms, meaning the mass term is not invariant under this. Therefore, everything works out if the photon is massless. And we are lucky, the photon is massless. Yeah, so this works. Great. However, the problem comes now. This is the particle content of the standard model. I say here as of 2011. I don't have to describe the quarks, electrons, and all the gauge particles. You know this. As I said, it predicts massless gauge photons. However, we know that particularly the Z, the W plus and the W minus are massive particles. We know this from the experiment. So they can't be described with this kind of construction principle. It doesn't work. The explicit mass terms break the gauge barriers. And people thought for a long time how to solve this kind of problem. And the one solution that really worked out and also survived all the tests is the Higgs mechanism, or sometimes people also say Prout-Anglia-Higgs mechanism. And the idea is that you postulate that there is a new scalar field, and the mass terms, they are not written explicitly, but they arise from the coupling of this new field to the other particles. And you will see in a moment how this works out. In the standard model, we take an SU2 doublet, a complex doublet with 4 degrees of freedom. So every entry here is a complex entry. The Higgs potential that I can write down is spelled out here, just the quadratic and the quartic term. The potential must be bounded from below so that you don't fall into minus infinity. Therefore, the lambda must be positive. And the new term here, the square, can be either positive or negative. And this is a choice that in the standard model we assume must do by hand. And this you know from high school and only from 10, when you were 14, 15, you had this in school. If the mu squared is positive, you find this shape. And if the mu squared term is negative, you find this shape. Right? This is something very elementary. And if mu squared is negative, the minimum of the potential is found what we call just at this value. And then we introduce this new letter here, V, the vacuum expectation value. It's the distance in field space where this minimum is found. Good. How does this help us? Does it help us at all? We'll see how it helps. We go to a very simple picture again without any details, where we remove the other degrees of freedom. I'll come back to this in a moment. And this complex doublet that I introduced, the capital I, is just written down like this, like the V that we had introduced here, plus the Higgs boson, the elementary scalar field. The Lagrange density for the Higgs, well, this is the kinetic term. Yeah, it's as usual, d mu phi, bigger d mu phi. Then here we have the couplings of the Higgs to the SU2 doublet QL, which I've written down here, which contains the two quarks, QL and DL, times the R, and the term which is called here, has here this phi sub c. I'll come back to this in a moment, where we couple it to the uptime quarks and then the potential. That's shown to you before. Now, the derivative contains the normal derivative and the gauge fields that are introduced in the standard model that so far are massless. They don't have any mass. And we will see in a moment how the mass then arises for them. As I said, here in this part, we couple the Higgs to the gauge fields because they appear here. And here we couple the Higgs to the particles. And both of these terms, as we will see in a moment, give rise to the mass terms that we are after. You can imagine up here, if I take the phi, and I can either use on the phi the V or the H. And if I use here the V and here also the V, then I get a term like gauge field times V times gauge field times V, meaning gauge field squared times V squared, and this is by definition the mass term, exactly how I had introduced before for the photons. That didn't work. But here the mass term now arises from the interaction. And also here we take this doublet, the QL, that's the form here. You multiply this QL with the pi, you see 0 times QL gives you nothing, but DL times V times the R is exactly a mass term like we had it for the electron in the Lagrange before. Now the question arises, how can you do it for the uptight quarks? Because the uptight quarks are upstairs and the left is downstairs. There's a little trick, sorry that you can play. You take the complex conjugate, you multiply it with the second Pauli matrix, which is 0 minus phi 0, which just flips the two entries and thus moves the upstairs. And then with this term, this I sub c multiplies UL and then the R and gives you the mass term that you desire. And then you get these mass terms for gauge bosons and fermions. And to show it in a bit more graphical way, can you see like this? You start out with a massless gauge boson, and now you couple the massless gauge boson to the left. I told you have to couple it twice to the left. Yeah, so on this here, you always take the left here, and then this kind of term where the gauge boson coupling twice to the left. But you live in a quantum world. This does not happen only once, it can happen twice, 3 times, etc. So you have to add this type of interaction and then 3 times and 4 times and so on. Now, the massless gauge boson, the propagation is described via 1 over q squared, q is the momentum of the gauge boson. And then when you add up all these terms, you find, for example, for this term here, you first have the propagation of a massless field. You have the interaction with the left squared. Here. This is the coupling constant. And then again, you have the propagation of the masses. And this you can have once when j equals 1, twice, 3 times, etc. And this you should also know from school. This is just a geometric series that you evaluated. You find exactly this impression, meaning this massless propagator now has this form, and this m squared is given by the coupling constant squared v squared divided by 2. That's just this geometric series summed up. And the important part here is that the m, the mass of the particle, is exactly proportional to the coupling of the particle to the Higgs. Yeah? G here is the coupling constant, and it's important that m is proportional to G. For fermions, it works equally well. I don't say it in so many details. We start out with 1 over q slash, And then you get this 1/2/-F. And also here we have F is given by the coupling constant of the Higgs to the fermion, GF times V divided by square root of 2. And also here, we find that the mass of the particle, the MF, is proportional to the coupling constant. And this is a very profound prediction of the Higgs mechanism. And when we say we want to test the Higgs mechanism, this is exactly what people are doing, what Atlas and CNS are doing for the last 10 years. After the discovery of the Higgs, they're testing out this kind of relations. Good. Finally, the mass of the Higgs boson itself, the self-coupling. You have a quartic term, but also here you can replace the Higgs twice by that, and then you get out Higgs squared times Z squared, again a mass term for the Higgs boson. And this was like this. The Higgs mass is given like the left times the square root of this lambda, and lambda was this parameter in the potential, and it was an unknown height. We didn't know it, and therefore the Higgs mass in the standard model is not known, or was not known. Now we've measured it. Now we know it. So this is the final mass that we needed, and therefore establishing the Higgs mechanism is not only finding the Higgs, but measuring all its couplings. This is the question. Now I think comes the first question for you. So, how can you measure the couplings? And maybe are there other things that you are supposed to measure in order to identify the Higgs mechanism? How do you think you can measure a coupling? Yeah, Higgs. What happens with the Higgs? You take it home. How long does the Higgs live? Actually, I don't know. But you have here outside this nice picture of CMS, yeah, and the Higgs is produced there. It effectively instantly disintegrates. And I told you that the coupling of the Higgs to a particle is proportional to its own mass. And therefore, the strength of the decay of the Higgs to a particle should also be proportional to its mass. And therefore, one has to try to measure all these relative decays of the Higgs boson, and this should be the proportional to the mass. This is the idea. Is there anything else that one should try to measure? For example, I told you it's a scalar particle. One should try to measure whether it's a scalar particle. I will not talk about this today. This is one of the other. We'll come about to the BSM physics in a moment, but this is one of the other important quantities that I have to explain. So, no answer from your side. You should think about these things. And I have more questions. Now, I will briefly introduce another effect of the Higgs that was known long before the Higgs was discovered, but that also, I mean, as you said, I did my PhD in '98, so this was long before the Higgs was discovered, but it gave me confidence in the Higgs mechanism already those days, that there's something behind. And this concerns the scattering of W bosons. So you look at the process, WW goes to WW, whatever here. This kind of process, WW goes to WW. And in your theory, how can this happen? Well, you can exchange here a photon or a second. Also exchange here a photon. And finally, there's this quartic. Yeah, we have 4 W's. Now you calculate the amplitude of the probability for the process is the amplitude squared. But the amplitude is given here by coupling constant squared, E squared, which is the energy of incoming electrons, divided by the mass of the W. Okay. And this is the limit for large hydrogens. Y eso es peligroso. Pero porque es peligroso. Si la probabilidad crece con la energía, ¿qué es la probabilidad máxima de algo? 1. Exacto, 1. Y si crece con la energía, in un momento crece encima de uno. No debe ser. Oh, sorry. Yeah. So, thanks. This growth with energy goes above 1, and then I shouldn't write this in. Violates mathematics. Yeah, unitarity, you think. Can't be. But now, what happens if you introduce an additional scalar particle, which I tentatively here already H? We have two more diagrams, this one here and this one. Again, you can calculate the amplitude, and you find that it's the coupling, the Higgs, the gauge boson squared, energy squared divided by mw to the 4. And of course, you have to sum up everything. You sum up these terms, and then you find this relation. You find this dangerous part with this prefactor. And of course, this prefactor vanishes exactly when this condition is given. Yeah, when the coupling of the Higgs to the gauge bosons is given by the coupling constant times the mass of the particle. And this is exactly the coupling that the Higgs mechanism predicts. Yeah, so the Higgs mechanism cures this problem automatically. Very nice. And I have a nice graphic for this, which I stole from a friend of mine, who stole it from another friend of mine. And this is not the Nobel Prize winner, it's a German physicist, a theorist working in the UK. And he's also not related, I asked. But he did this nice plot where he shows here the center of mass energy for the incoming W's, and this is cross section. And if you only look at QED, you only have the photon. Then you find this curve, which is now you include also the Z and the quartica, like the red curve. It behaves better, but then still. And only when you include also the Higgs contributions, you find this falling possibly. Everything is okay. Yeah, so the Higgs cures this. This was done for 100 GeV Higgs, but it doesn't matter. It works equally for 100. Good. So the Higgs also solved this. Now, I don't know whether you must have seen these plots, but they are so beautiful. I can't see them often enough. These plots were presented by Atlas and CLS on the 4th of July 2012, and we were actually, well, I don't know, I'm not sure, we were sitting in this very room seeing the live transmission in CERN where these plots were presented. And what do they show? They show what they call the local P level, which means the probability that what you see is background only, meaning standard model without any Higgs. And the probability that if you don't see anything, it should be around 1/2. And this is a function of the mass of the Higgs boson. And one sees that here there's a drop in the probability, meaning what you see is background only has a probability of 10 to the minus 9. Effectively impossible, meaning there must be something like this. And this was Atlas, this was CNS. They also nicely put the sigma level. Singapore, they had sigma, they had the high sigma, luckily at the same mass, meaning there was a discovery. So the discovery of the Higgs boson was presented on the 4th of July 2012. But what is it, obviously? Is it a Higgs boson? Is it the Higgs boson of the stellar model? Maybe it's a symmetric Higgs boson of a different model. Maybe it's a particle that only looks like Higgs but doesn't have anything to do with the Higgs mechanism, which was those days called imposter. How can we decide? Well, we have to measure all its characteristics and compare the predictions, the various models, with the measured quantities. Yeah? So this is, let's say, one part of the answer, and the second part of the answer, in order to see whether there are other models. I come back to this in a moment. We have to search for additional Higgs bosons above and also below 100. So we find the second Higgs, of course, the standard model is obviously ruled out. It is ruled out anyway, as I would say. Good. So we need precise predictions for all the Higgs boson properties. This is just to show you what experiments are after. This is something that you should have seen in the class already. These are these partial widths, the decay strength, let's say, of the Higgs to a certain final state, B for decay, not for downfall. It's just the decay particle in sum of all d prime. And you could have, in principle, of course, Higgs to T bar, D bar, C bar, etc. Then to leptons, to gauge bosons, possibly off shell, etc. And this quantity that I was alluding to before, that tells you something about the coupling in the end, is the branching ratio. The branching ratio is the probability that the particle decays to a certain state. It's the partial width divided by the total. And by definition, you see here, the sum of all the branching ratios must be 1. From the construction. And this plot was done in 2000, well, it was 2013, but the first versions were done in 2011, also before the Higgs discovery, when we didn't know what is the mass of Higgs boson, and we prepared for everything. And so we started at a value of 80 GeV up to 1000 GeV. And then this is the branching ratio. And the, well, look, for example, there's a colored band, let's say here, the green one, which has a black center. The central line is the prediction. The band tells you the theoretical uncertainty. And one can see that here for low masses, the decays to fermions is dominant, also gluon, and then here the very low probabilities, photon, Z gamma, or mu. And when the gauge bosons can be, when the decay can be on shell, so 180, 160 GeV, these decay modes dominate. This is then TT bar that can also be important. So when you don't know the Higgs mass, and maybe, yeah, you can imagine if the Higgs mass is very low, you can measure all these decay modes, but we don't have access to these ones. If the Higgs mass is very high, you could only measure these decay modes, but not those ones. Very bad. And nature was very kind to us. This is a zoom for between now 80 and 200. We know that the Higgs mass is 125. We are so lucky. We have nearly all the decay modes that are possible. Only TT bar can't be accessed directly, but we can get this via fraction of the Higgs. But the mass of 125 really allows us to measure all these various elements. I think nearly all of them have already a central value. I think this is the only one where we only have an upper limit. So it's really very nice. See, some of the gamma, although it has a very low branching ratio, 2 times 10 to the minus 3, it's so clean, this decay mode, that it was one of the 2 discovery modes in 2012, together with the one in ZZ, and then also with the help of WI. Yep. One more word about the production at the LHC. You may wonder, how can we produce these Higgs bosons at the LHC? So there is the main production mode, gluon fusion. So we take the protons out of each proton, we take a gluon. We have the top triangle here, and then the top gives Higgs. And although this is a loop-induced process, which is normally suppressed as a loop, the coupling of the Higgs to the top quark is so strong, and also the strong coupling force is very large, that this is actually the largest production process. The second largest one is this weak boson fusion, where you radiate from quarks either WW or ZZ, increasing then the Higgs. You can have this radiation from a gauge boson, or you can have the radiation from a heavy quark, like top quark, also bottom quark is possible. These are the various modes. And this is for 8 TeV, but it looks very similar for 30 TeV. I think now we have 13.6 TeV at the LHC, but the overall picture is the same, only change the scale here. This is this blue Higgs node. Yeah, this is really the largest one. Then this here is the one with a weak boson fusion, radiation from W, from Z, and from TT. Yeah, so they stand in various orders of magnitude, but this is really the dominating. Good. Now we come back. Start with the second part. you can say, standard model works great, everything looks fine. Yeah, we have this discovery, and we even have a standard model like this. These are the most recent measurements presented by partners in CNS, always normalized to the standard model. Here, the cross-section normalized to the standard model values. So one is the standard model, and these are the various modes: dual fusion, deep boson fusion, WH, ZH, and TTH, and it's always compatible. Very good. Similar here for CNS, where they also have the decay modes here. Yeah, decay to photons and ZWW to tau and mu. It's always one. Standard model seems to work. Can we go home? Well, I have a second fact for you. We know that the standard model cannot be the ultimate truth. And these are some facts of this one. Therefore, play a role in the moment, or some of them will play a role in the moment. Gravity is not included. Yeah, so standard model is certainly not complete. We have the hierarchy problem. I'll tell you in a moment what this means. In short words, it's the instability of the Higgs mass with respect to quantum corrections. But I'll show you how it works. We don't have unification of three forces. They're all independent. We have no dark matter candidate, very important for the IFCA, which is involved very much on all sides in dark matter analysis and investigations. We don't know why there's more matter than antimatter in the universe. Can't be explained with the standard model. Neutrino masses are not included. And there are some experimental data that are not included in standard model prediction. And one of them is possibly the enormous magnetic moment of the muon, which I'll show you. Good, so these are several facts, and so I will explain some of them in a little bit more detail, not much, but a little bit more detail. Let's start with the hierarchy problem. Mass is what determines the properties of the pre-propagation of particles. Pre-propagation is shown here, and in quantum field theory, this is given by the so-called propagator, where the inverse propagator is I times p squared minus mass squared, meaning the mass of the particle, p squared is the formal momentum that is flowing here, and this in quantum mechanics of quantum field theory describes the propagation of the free particle. Sorry. Now, this is the simple picture here that doesn't take into account that we're living in a quantum world. We live in a quantum world, there are quantum corrections everywhere. And one important quantum correction that happens here is that Higgs can disintegrate for a moment to a pair of fermions, for example, and then the closer level Higgs continues to live. And this kind of loop gives a contribution to this inverse propagator indicated here. Sigma is just this kind of loop correction of Higgs given by this quantum world. Now, as I said, we live in a quantum world, we don't know which momentum is running around here. And in quantum mechanics, what you do always, if you have many, many options, you just sum them up. And this is the integral over the momentum that is running around in the loop here. So the contribution that you get to this inverse propagator, sigma, is given by the, let's say, the number of these, or color of the number of colors for the number of fermion, the coupling constant squared, and then the integral, without going into too many details, it contains the term that goes like 1 over k squared, minus ms squared, plus this additional term. And if you look at this in a little bit more detail, you find these two terms. First, integration in Minkowski space v for k divided by k squared plus 2ms squared dk over k. Now, the argument always goes like this. This integral goes from 0 to infinity. But to infinity doesn't make sense because we know that the theory is not valid up to infinity. We know, however, that the theory is valid probably to the Planck scale or something like this. Yeah? So the integral should be performed as an upper limit up to this scale until the theory is valid. We call it capital lambda. And if you just look at one possible capital lambda, you see that this piece here diverges with the lambda squared, this piece here goes logarithmically with m. And this is what I call quadratically divergent. There's a method to cure this. I'll come back to this in a moment, but the corrections that you receive to the Higgs boson mass, this is a correction to the Higgs boson mass. It's here that goes quadratically with this high mass scale squared, and if it's the Planck mass is 10 to the 18, Higgs mass is 10 to the 2. You get corrections that are 10 to the 16 squared, larger than the mass itself. This doesn't look very natural. It can work out, but it doesn't look natural at all because you need cancellations over 30 orders of magnitude or so, and therefore it's divergent. This is what I just told you is also here. These large directions. Okay, I think we can skip this. The problem is there's no symmetry that protects the low Higgs boson. It's not only zero or small Higgs boson mass. You can say the photon has mass zero. What happens to the quantum connections? Well, the symmetry of the model, the U1 that gives you the photon, protects the photon mass, and all these corrections that you calculate come out to be zero, thanks to this U1 symmetry. If you look at fermions, the electron is very light. What happens to the corrections to the electron? Calculate them, they all go like log of lambda divided by the fermion mass. So it's only logarithmically increasing and therefore dangerous. But here we find these quadratic corrections, and these are the dangerous ones. So no protection against large corrections. Cold dark matter. Just one plot to show how it looks like. This here is the plane of the dark matter quantum of the matter quantum of the universe, omega n, and different convolution called omega lambda, which now we call dark energy. And there are several measurements. It's an older plot already, but the newer plots look the same, only that I didn't find them that nice. Where one has several measurements in this plane where we are. So this line shows you corresponds to flat universe, and the cosmic microwave background measurements tell you that we should be somewhere along this line. You can measure the behavior of supernovae, and then this is how clusters behave. You find that all these three measurements intersect in one point here. Well, we find that this is always relative to the critical density, corresponding to the universe. The total density is about 1, this comes out right. Then we have a meta density shown here, and we can also look what is the density of all the atoms and the stars in the element. It's called baryonic density. This can be just measured by looking at it. And you get this number here, and you see that there's a discrepancy between numbers. And this is then attributed to dark matter. Yeah, some matter that must be there that interacts gravitationally, but is not visible. It's here, and then also this omega lambda, the dark energy. The important part is that we have this dark matter contribution, matter that we can't see, and only acts gravitationally, and the standard model doesn't have any candidate to this. Just can't account for this. Finally, I will say a few words about the enormous magnetic moment of the muon. Maybe I show first this one, and then I come back to the other one. This is the experiment. Schematically, I think this is how it was done about 20 years ago at Brookhaven Lab, and how it's now done at Fermi Lab as well. You take protons, the target, you get out ions, the ions decay to muons, and the muons are added into a storage ring. And the storage ring is actually quite small, 40 meters. I saw it once 20 years ago. Brookhaven Lab, you go to a hall, you can just see the holes. It's very impressive. Not like the LHC. And you see that here we have the muons indicated as little cones, and then this arrow going around, showing that the spin direction should be oriented with the direction of light. But there is a little misalignment between the direction of light and spin direction, indicated by this cone that is slightly misaligned. Well, the muon decays, of course, decays into muon neutrino, electron, antineutrino, but you can measure only the electrons indicated here. The electron goes to detector by the angular distribution of the electrons that you see here. You can get the information or what you are after. I've written down here the interaction. Well, how you get the muon on the circle. Yeah, it circulates around here, you get it on the circle, and the magnetic field means the interaction with the photon. It's just electromagnetic interaction. You have here muon, then you have here the muon with the photon, and this is the model Lagrangian, corresponding to the QED example that I had shown to you before. There is the second part that are from the meters is proportional to the momentum here, sigma mu times q, and then this F2 is a contribution that arises only at the loop level. I'll show you later how this works out. And this deviation from the normal piece that we expect from the QED type Lagrangian, this one here, it's called the anomalous magnetic moment of the muon. So this piece here is measured accidentally, and it was measured by Brookhaven lab. Kawasi said that I was postdoc there. I was really lucky. I was postdoc there when this was presented for the first time. It was a very exciting time. And we have a prediction in the standard model. And we have this measurement here. And this showed the discrepancy of 3.7 sigma. Now, about 2 years ago, the new experiment at Fermilab found out this value here, which is fully compatible with the old one. And then you can average them, then you find the discrepancy of 4.2 sigma. In numbers, we talk about the quantity at the level of 10 to the minus 10, which is impressive by itself. Yeah, imagine a theory that gives you a prediction at the level of 10 to the minus 10, and an experiment that gives you a prediction of 10 to the minus 10, and then you find it. This is really remarkable. And this is the difference here at the level of the 4 sigma. And we are waiting. What Fermilab has presented was the first run, the date of the first run, and now we are waiting for this year later, second and third run. So they will substantially improve the experimental precision. Now I will skip these details probably. Let me say this. This is one contribution. We always look at the coupling of the muon with the photon. And then there can be corrections like this one here. And here we have the correction where we have a photon exchange. And the photon again has this loop with the Fermi. And this is a problematic part of the theory prediction because it depends strongly on the mass of the quark. And the mass of the light quarks we do not know very well. And this introduces a large uncertainty. Therefore, what people do, they take this piece here from the experiment, they look at E plus and minus, going to photon, going to hadrons, going to quarks. They take some experimental measurement and insert it into the theory. And then this gives you an answer. However, there's an alternative method to do this kind of calculation, which is based on lattice QCD, LQCD. And there seems to be some disagreement. These are 3 evaluations that were done based on this method, taking experimental data, and then there is this result from lattice QCD that it's using a completely alternative method complicated. It's not going to too many details. And the point is that only this kind of evaluation gives you a large discrepancy with respect to the standard model. This is substantially closer. And we are waiting now that the other lattice groups give a similar precision. They're working on this, and so far the situation is unclear. One can go to many details, which I will not do here, but there's no reason to say this is right and this is wrong, or the other way around. It's just an open question of what's going on. And if this was correct, then other problems in the standard model would show up. There would be problems with other precision data, etc. But I said I will not go into. If one takes the so far world average based on the previous method, we find this 4.2 sigma. Otherwise, we are now at the higher precision, a little bit less than 2 sigma. Okay, I told you a little bit about the problems that the standard model has. And if we take these facts 1 and 2 together, there's only one possible conclusion. The Higgs that we've seen cannot be the standard model Higgs. This is just not possible because the standard model is not the final answer. However, the real question that we want to ask is, does the BSM that must exist, there's no way around, does it have any relevant impact? And if so, maybe which model might be preferred? And the answers I gave to you before, partially, we have to look for the changed properties of the Higgs boson. We have to look for additional Higgs bosons, and this you have to look above and below 125. Good. Now, models with extended Higgs centers. I think I have another question. Can you name any BSM model? Any. Supersymmetry, we will come to supersymmetry. Very good. Other models.
Single extension.
You know all this, I know, yeah. It's part of this Trabajo index. Yes, yes. So, yeah, the standard model, you can add singlets, meaning more Higgses that do not interact. You can add a second doublet, then you have 2 Higgs doublets. You can have the SUSY version, the minimum standard model. You can have the SUSY version with additional extra thing, 1 or more. You can have triplets, etc. And then there are also models without extended Higgs centers, but that have still changed properties of the Higgs bosons because the quantum corrections that I showed you before. If the model has a different particle content, it will give you different quantum corrections. And therefore also a model that has only 1 Higgs, but other BSM particles the standard model does not have, will have changed Higgs properties. Yeah? For example, you can add vector-like fermions, you can have Higgs radiants, etc. Good. So there are many, many models. And the question is, which model should we focus on? And they all say, well, take experimental data as guidance. Experimental data is always good. And I have here 4 recent, very quotation marks, measurements. We have the mass of the top quark that has been measured now 20 years ago. Something, the first measurement came out about 20 years ago. Oh, no, even more.
In 1905 it was discovered. So
Yeah, okay, yeah. We're getting old. We have the mass of the Higgs boson. We have the Higgs boson couplings, and we know something about the dark matter properties, we know the relic density, etc. Now, if one looks at very simple supersymmetric extension of the standard model, and without going into many details, these models predicted, I stress the word predicted correctly the mass of the top quark, the mass of the Higgs boson, the Higgs boson couplings, and also the dark matter. Yeah, all this was done long. All these measurements were done and long before we knew the right dark matter densities, etc. And therefore, it's always a good motivation to look at this kind of models. I know that nowadays people are a bit disappointed by this model because they haven't seen anything, but all kinds of things. I don't think I have too much time. No? How much time do I have?
10 minutes at most.
10 minutes. Let's skip the. I think I'm talking too much. Let's skip the introduction to supersymmetry. Just the simplest model has here the standard model fermions, the quarks and the leptons, and then has the SUSY partners, which are effectively the same particles, just with different spin and different mass, the scalar quarks and the scalar. Here we have the standard model gauge bosons, but an extended Higgs sector. It's a Higgs doublet model. They all have spin 1 or spin 0, and the respective SUSY partners spin 1 out. So here we have Higgs doublets. I didn't tell you about the most important calculation in the standard model. In the standard model, we start out with 1 Higgs doublet. And these were 4 degrees of freedom, two complex statements, 4 degrees of freedom. And we have to give mass to 3 gauge bosons, the Z, the W plus, and the W minus. Each of them receives a degree of freedom when it gets its mass. Meaning, we start off with 4 degrees of freedom, 3 go to the mass of the gauge bosons, 4 minus 3 is 1. So you understand the most important calculation in this standard model. Here we start out with 2 doublets, 8 degrees of freedom. We still have to give mass to W plus, W minus, and Z. 8 minus 5, 8 minus 3 is 5. This is the most important calculation this type of model. So in this model, we have 5 physical Higgs bosons, not 1. Was 8 minus 3 is 5. And the lightest Higgs in this model is automatically or nearly automatically also standard model, like bringing in agreement with all the experimental. Okay, answered by the 5 Higgs bosons. This is particle content. And I can say this in one slide. It cures the hierarchy. We have these new particles here, the SUSY partners of the top one, for example, the scalar top. And we get these additional contributions. They also scale with this lambda squared. And if one does the calculation, one finds that if everything behaves according to SUSY, these dangerous terms, they automatically cancel each other. This was why SUSY was introduced to particle physics, the hierarchy. And it just works out well. Of course, one says SUSY should not be heavier than QTD, otherwise this solution doesn't work out anymore. But SUSY at the TD step provides an attractive solution to the hierarchy. Dark matter. This is a very old plot, but it still shows the important thing. These are 2 SUSY mass scales for permeable masses, for scalar masses. And one finds that in large part of the parameter space, the light greenish area here, SUSY gives you a good dark matter candidate. Actually, I'll show you which one it is. It's this one, the SUSY part of the photon, which is a good dark matter candidate and gives you the right dark matter density. Yeah, so SUSY predicted more or less what you can find as a relic density, and easily one finds exactly this relic density in your field. This works out very well. And unification of forces. This is the standard model picture on the left. We start off with 3 measurements of our 3 coupling constants. We evolve them to higher energies. And we see this is the problem why we don't have unification of standard model. They do not meet. There's no unification of forces. In SUSY theories, you see these lines, they bend a little bit. This is where the SUSY mass scale is located, and where there's an effect on the evolution of energy of these coupling constants. And suddenly they leave one function. So this was known since 92 or so, now 92. And it was one of the great triumphs, I would say, of the theory. It was not designed to do this, you just find out it works. I think automatic implication also in this kind of one. And finally, the anomalous magnetic moment of the muon. Also here we can have additional contributions. If you have a muon photon coupling, we have additional contributions from SUSY particles. And if you do this, this is the generic contribution. It's 13 times 10 to the minus 10 times some suppression with SUSY mass scale, etc. But we're exactly in the ballpark. We're exactly in the ballpark that is needed in order to get the deviation. Yeah. So also here, SUSY naturally gives you the right number. can do this problem. Good. And with this, I will conclude here. Is SUSY dead? Yeah, it's a famous quote from Mark Twain. And then you say, yeah, but what about all the experimental results? And indeed, the experimental results are a bit disappointing. Obviously, we all hope for the physics of the LHC. These are all the limits for the SUSY searches taken by Atlas. And you see here, all these limits are between half a TeV, 1 TeV, up to 2 TeV. We don't see it. And of course, this is not what we were hoping for. However, I have a very similar point. These are the exotic searches, meaning all other BSM searches not SUSY. And they differ only by color, I would say, yeah, but not by reach. Yeah? So, conclusion: SUSY is as dead or as alive as any other BSM. Yeah, this one should be. People are disappointed because they were hoping for something soon. It didn't happen. But there's no reason to say this theory is dead and the other one is better. Yeah, the limits are as severe in this one. And of course, one should on the theoretically most appealing theory. And these are some reasons that I list in the computer. I think it is nearly inconceivable that there's no symmetry with the back, and I didn't say this in detail. SUSY and symmetry between bosons and fermions connects spin 1/2 particles with the spin 1 or spin 0. And it's really inconceivable that in nature there's not such a symmetry. SUSY is the only non-trivial extension of the standard model in terms of symmetries. SUSY gives us coupling constant indication. As I predicted the top quantum mass correctly, predicted the Higgs boson mass correctly, predicted the properties of the Higgs boson correctly, and predicted the dark matter properties correctly. And I think this is still a very good argument to look at this. I'll not talk about this. I think I just made enough. I just conclude. The standard model is a highly successful theory, however, fails to explain certain things like gravity, problem, or function of forces, dark matter, function masses. Many BSM models exist. SUSY has overall the best features, fails to weight gravity, solves the Hardy problem, unifies the forces, natural dark matter candidate. Some models also include neutrino masses easily, and we can explain beyond. Looking at the experimental data, SUSY is as alive or dead as any other BSM theory, but it's only the only theory with all these nice features. And there is hope, I think, that in the electric researches, because of Q-2, you can see something at the LHC with the upcoming data. Thanks a lot. How does it work now?
Well, we let people, not non-students, who want to ask you any questions from outside of here, ask the questions. Then we take a small coffee break, and then we come back.
Exactly, this is what I remember from last. Very good, very good.
So other questions, not from students, that will get their long chance later.
On your previous slide, this is a new particle, the neutrino.
It's a SUSY version of the concrete.
It's like the biased version.
So this is perhaps slightly in a different direction, because I want to ask about composite Higgs models.
Oh,
but
yes,
But Higgs is not fundamental.
yes.
Can you say something about the current status of the?
Yes.
Or if you would like them to.
In these models, without going into too many details, what you're mainly looking for are deviations of the Higgs couplings to the standard model prediction. There are various types, either the couplings of all other particles to this Higgs in the composite Higgs model, they're modified with the same factor, or there are 2 or 3 different factors that you can look for. And as you know, or as everybody here knows, we haven't seen any deviations. And what people are doing is, as for SUSY, there's a scale, the composite scale, that goes higher and higher with time. Yeah. This is where we are. And yet you can set limits on the scale. And this is what people are doing. Yeah, there's no other progress that I know of.
Okay, so let's take a coffee break. Yes. And then we'll come back with the students.
Very good. Very good. Why would you put someone to
Okay.